Welcome to the solutions to the Regents Modern Physics problem set numbers 15 and 16. Let's get started with 15. A photon with an energy of 6.2 electron volts, so that's E, enters a mercury atom in the ground state. Will it be absorbed by the atom? See the mercury energy level diagram in your New York State reference table. So let's start by having that diagram in your reference table out. It's the same one pictured in this solution here. And what I'm going to do is I'm actually going to draw on this one. I wouldn't recommend that you do that in your reference table, but if you want to sketch it in your work, that would be fine. And so what we have is we have an electron in the ground state as described in the question, and we have a photon, and I don't know what color it is, but I'll just use blue, that comes in and enters the mercury atom while the electron is in its ground state. And we're told that that photon has an energy of 6.2 electron volts. Okay? Now, the question is, will that photon be absorbed? What it's asking is, is that energy just the right amount to excite it to a higher energy level? The answer to that question lies in the fact that in order to absorb that photon and the electron to get excited to a higher energy level, that photon's 6.2 electron volts has to be exactly equal to the difference between any two energy level transitions. Okay? So let's start with this. Is the 6.2 electron volts enough to ionize the electron in the ground state? And the answer is clearly no. That 10.38 electron volts right there is the ionization of the mercury atom in the ground state. 6.2 is not enough. Likewise, as we take a look at the rest of these numbers up through here, none of them match 6.2 electron volts. Okay? So, the only way that this photon gets absorbed is if the electron transitions from the ground state, A, up to a higher energy level, B, C, D, somewhere where the exact energy level difference between those two is 6.2 electron volts. So now we're just going to use method of elimination to see if we can figure this out. So we're going to look at how much energy is required to transition from A to B. Well, this would be very simple. 10.38 minus, in B, it would have 5.74. Well, when we subtract, go ahead and do that on your calculator. Pause the video if you need to. We get 4.64 electron volts. This certainly does not match 6.2. All right, what does that mean? Maybe it's to a higher energy level, making the difference greater. Let's check from A to C. 10.38 minus, how much in C? 5.52 equals, pause if you need time to calculate, 4.86 electron volt. Still not enough. Let's check A to D. 10.38 minus, in the D state, it would be 4.95 equals, pause if you need time to calculate, 5.43 electron volts. Still not enough. What about from A to E? 10.38. In the E state, it would be 3.71 equals, pause if you need, 6.67 electron volts. So you can see that the value of the entering photon of 6.2 electron volts lies between these two values. What that means is that this photon cannot be absorbed. So the answer is no. Okay? The photon cannot be absorbed because it is not exactly equal to the difference between two energy level transitions. Okay? That's the answer to 15. Alrighty, let's move on to 16. And this says, the diagram below shows the energy levels of a certain atom. If an electron can make transitions between any two levels, how many spectral lines can the atom emit? Which transition produces a photon with the highest energy? As we can tell by looking at the diagram, what we're going to do this in a systematic way, and it doesn't matter what order you go in here, but you have to do this in a systematic way. The first thing that we note is if it says, if an electron can make transitions between any two levels, how many spectral lines can the atom, keyword, emit? What does that mean? That means the electrons have to be traveling down in the energy level diagram, or do the electrons have to be traveling up in the energy level diagram? In order to emit the photons, the electrons have to be traveling down. So what I would propose is that we start with an electron in the E equals 4 state and look at how many possible spectral lines can be emitted here. So we go from E4 directly all the way down to ground. That would give off a photon. From E4 to E2, that would give off a photon. And from E4 to E3, that would give off a photon. And we've covered all the possible transitions from E4. Next, we start with an electron in E3, which if it dropped by itself all the way to ground, it would emit that photon. From E3 to E2, it would emit that photon. And what other possibilities exist? From E2 to E1 directly, and it would emit that photon. Have we covered all the possibilities? The answer is yes, because if you take a look, for example, at E4 to E2, it would drop to E2, and then from E2 to E1, and we already covered that. From E4 to E3, it could then go from E3 to E1, E3 to E2, and we've already covered those possibilities. From E3 to E2, we've already covered that possibility from E2 to E1. So this is it. How many total spectral lines? 1, 2, 3, 4, 5, and 6. So 6 possible spectral lines, okay, in this energy level diagram. Last question. Which transition produces the photon with the highest energy? The answer to that is going to be the transition with the highest energy level difference. Okay? So we want the transition with the highest energy level transition. And what would that be? Well, according to the diagram, the one with the greatest energy level difference would be E4, transition down to ground state E1. These are the solutions for questions 15 and 16, and we'll do more problems in class.